Another hyperparameter is about how to split on a given feature. For instance, if a feature varies between 10 and 0, let's say, do I split at 5 or 3 or 7? How you split on a given feature will affect the model's performance. So we need a good measure of the quality of a split in a cart. This measure also determines the variable importance ranking that we saw earlier. Ideally, each split should produce pure nodes. In other words, we want to perfectly separate diabetic from non-diabetic people. And one very popular and often the default choice is the Gini index. Impurity of a node is calculated based on the relative frequencies of each class in the node. To understand cart fully, let's try to dig into the formula for the Gini index. The Gini index is denoted by capital G, and for binary classification, its formula can be simplified as follows. In this formula, I is the index for a node. Pi is the percentage of class 1 data points in the node. So 1 minus Pi must mean the percentage of class 0 data points in the same node. The best case scenario is when Pi is equal to 1, or 1 minus Pi is equal to 1. So let's say Pi is equal to 1. It means in the given node, 100% of the data points corresponds to class 1. Then if you look at the formula, we have 1 minus 1 squared, and then minus 0. So Gi is equal to 0. So a perfectly pure node has a Gini index of 0. An impure node is when you have an equal ratio of class 1 and class 0 data points in the node, because this means we haven't separated the two classes at all. Then, according to the formula, we have 1 minus 0.5 squared minus another 0.5 squared, which results in Gi equal to 0.5. So a perfectly impure node has a Gini index of 0.5. Another popular measure of impurity is the entropy measure, which originates from thermodynamics. Entropy uses a different formula than the Gini index, which involves the use of the log function. Another main difference between the Gini index and the entropy measure is that entropy is bounded between 0 and 1, 0 representing a perfectly pure node and 1 representing a perfectly impure node, instead of being bounded between 0 and 0.5, as it is the case for the Gini index. But many people prefer to use the Gini index because it's faster to compute, and it's faster precisely because it doesn't have the log function. But I want to leave this slide with a statement from one of the most well-known data science textbooks. The truth is, most of the time, it does not make a big difference. They lead to similar trees. Gini impurity, as I said, is slightly faster to compute, so it's a good default. Before we talk about cross-validation, I want to first address the issue of class imbalance. In our exploratory data analysis, we saw that there were fewer class 1 data points than class 0 data points. So why does this matter at all? If we don't do anything about it, then our model is naturally trained more towards predicting class 0 data points better than it predicts class 1 data points. This can be problematic depending on the application, but in our application, it is problematic. Remember that we want a model which is good at predicting whether a person has diabetes. If our model falsely predicts that a person doesn't have diabetes because it is more trained to predict class 0, but the person actually has diabetes, the consequences can be critical in reality. So we must do something to make our model predict class 1 better, hopefully without affecting its performance on class 0 too much. A simple way to do this is to assign greater weights to the minority class. In our case, that's class 1, so that when the model classifies class 1 data points wrong, its contribution to cost is higher. So we naturally nudge the model to focus just as much on class 1 as it does on class 0. In R, we can do this using the following code. In the third line, notice that if outcome is equal to 0, we are giving it a weight of 0.35, which was the ratio of class 1 data points in our data set. If the data point is class 1, it receives a weight of 0.65. So this is how we balance the two classes. There are other ways to address class imbalance. Here I presented the simplest way, but other approaches include randomly oversampling the minority class or undersampling the majority class. In these methods, you randomly duplicate data points so that the ratio of both classes become equal.